All right, everybody. Welcome to lecture number 3. So before each lecture in class, I'm having pre-announcements by students who have things they want to bring up. If you have such a request, let me know. I'll throw them in the webcast. I won't actually read them here, but they'll always be available on the web as an archive of things people cared about in the year 2016, oh so long ago. All right. So I will mention that as part of this lecture, there's some coding exercises. You may find it useful as you're watching this video to have that code available. So if you go to the website, cs61b.ug, and click on the code link, you can get all the things you need. And if you are somebody who has a fair amount of Java experience, you might find it interesting to actually not watch this lecture or watch it on like 2x speed, but only kind of half pay attention after you have done these so-called exercises hard mode. Because what I'm going to do in lecture today is basically just fill out all the code in this section. Now that only applies, by the way, to the second half of the lecture. The first half is a review of primitive and reference types, which is something you may not have heard of before. Okay, but just so you know, when we get to int lists, you can just try it all on your own. Next up, Project Zero is due this Friday, and I want to give you guys some important information about our collaboration policy. So we've posted the course info page that lists all the policies of the class, everything you might want to know about late dates and all that stuff, how late scoring works for projects. But the most important thing for us right now is to make sure that we are on the same page about what collaboration means in our class. Okay? So there's 3 core rules. The summary of the longer policy is as follows. When you are submitting code in this class, your code must be by you alone. Okay? Every bit of code you write must be written, and in this case, you is plural, so if you have a partner, it counts as both of you. You should not be going to, say, Chegg.com and paying someone to do your homework, which has happened in this class. And it turns out we can get that code. Not that hard. Yeah, shouldn't be, your best buddy, whatever it may be. Your code's got to be yours. And the only exception is if you're looking up something like, how do I convert string to integer? And you copy a code snippet from Stack Overflow, that's okay. But whenever you do things like that, it's always a good idea to cite your sources. So we'll do rule number 3 next. So when you get significant assistance on an assignment, and I'll let you decide what constitutes significant assistance, you should cite those people in your source code. If you are using, say, song files you've gotten from the internet, you should cite those. You'll notice, for example, at the end of my lecture slides, I always cite all of the things I do because I think it's important that everybody gets credit for the cool stuff they draw, or produce or code or whatever. And it's important so that people know what work is yours. So I will say that this citation, right, even if it's something like I was totally brutally stuck on InBody, I couldn't even figure out how to read in files, and this person helped me out. It's nice to even cite that, I'd say. Okay? But the most important thing about citations, the thing that will be absolutely absolutist about, it's the best phrase I could think of, is that whenever you're using someone else's code, no matter how small, you must cite. If you're using a Stack Overflow thing, say, I use this post. Okay? Just good practice. And a very, very important one, right? And the one that is going to cause some number of people to fail the class is this one. Don't possess or share other people's code. There's no reason you should ever be sending anybody else your project code, that you should be going to look for solutions out on the web. You should not ever ask anybody, please just give me your code, I'm stuck. And you should never give someone that code. And the rule in this class is that if you happen to either give or receive such code, if you're turning in anything for a project that's not yours, or that you've given out to somebody else and we catch someone else and you're the source, then we're just going to keep things simple this semester. You will just fail the class. In the past, we've had slightly more complicated cheating policies, but it's actually quite a lot of work. So in this case, because Berkeley will actually let you retake a class that you fail for cheating, all right, I'm just going to have no mercy because you can just come back next semester. Sorry, I don't mean to be mean, but it's just I'd rather spend time with people who want to be in the class. So for logistical convenience, if you cheat on an exam, no matter how small, or cheat on a project, you just fail. Okay. Labs and homeworks, you also should not cheat. We will not insta-fail you. We are going to keep things slightly, read the course info. If you're thinking about cheating on a homework or a lab, but please don't. What's the point? They're so small. Okay. Lab 2 was actually already up, by the way, because I'm actually, I don't know. I'm not sure what time of day you're thinking this video is recorded or posted, but actually secretly it's Tuesday right now. But anyway, Lab 2 is up already. And so if you want to finish lab and avoid attendance, just make sure to turn it in by Wednesday at 10 p.m. And as a last note, if you have not taken 61A or 61AS, we're going to be doing some recursive code today. We're going to be working with recursive data structures. So you may find today particularly daunting, but I think if you do all the exercises, you should be fine. And we'll have extra practice, not just in lecture today, but also in lab and also in discussion. And also Project 1, really. So that's that, and this is no longer applicable since hopefully everybody's got a partner by now. So let's get going on today's lecture. So today is about primarily references and recursion. In Java, it turns out variables will come of two types. We'll see they're called primitive and reference types. And once we understand what those are, we'll be able to build really neat recursive data structures, linked lists, if you know what those are. And we'll have a little side syntax lesson. Oh, and if you're wondering what this guy is, so there was this residence hall at Berkeley called Barrington Hall back in the 80s and earlier. And this was a magazine they had. This is a Barrington Bull. You should read about it sometime. Interesting spot. I mean, of course, it's part of the long, interesting history of Berkeley. But yes, I had a very good friend who lived there, who sadly no longer exists in the universe. So this is an honor of Chris. We're going to kick off today with a quick lesson about the word public and what it means, and the alternate, which is private. And later we'll see there's even more keywords. So let's look here at our dog launcher and dog methods. This is the first version from last lecture. Here, the dog class, whenever someone invokes the make noise method, it will bark. And what dog launcher does is it just takes the dog class and tells it to run this public static method. So what public actually means here is that this method can be used by other classes. So there's another thing we can do instead called private. So if we make this private, that means it cannot be used by other classes. That is, if we have public, any dog can call this method. But here, whenever we have a private method, we're saying no other class is allowed to access this method. And indeed, when we try and compile it, we'll get make noise has private access in dog, right? It's a secret function or a secret method that only dogs are allowed to access. The outside world can't see them. So in other words, the private keyword in Java, the only thing it does is it takes an otherwise functional program and it breaks it. That's it, breaks programs. So that might seem kind of silly, but there's a good reason for it. What it does is it lets us write whatever functions we want here and not have to worry about anybody out there, one, relying on them, or two, having to understand them. So in other words, what we could do is hide all these little funny details from users of our class. So as an example, let's take walruses, which we'll have later today. So walruses, as far as the public API goes, if you're a walrus owner, it has a mouth, and you can pat it on the head. But it also has all these internals, like its organs. And you don't really think about those whenever you're interacting with your walrus, but they're nonetheless there. So it's less for the user of the class to understand. I feed the walrus. I don't have to worry about ATP and whatever else going on inside the walrus. And it also means it's safe for us to change the private methods. So I can replace the insides of my walrus with cyborg implants. And that's okay. It's not going to affect how I interact with my pet walrus. As a less tortured analogy, let's discuss the familiar automobile. So presumably you've either driven or seen a car and know roughly how they work. And so there's a public-facing interface in the sense that that's what the user is thinking about. There's pedals, which adjust the speed, and the steering wheel, which adjusts your heading. Then there's also all of these private things. These layers of interfaces, these interlocking pieces that you as the driver of a car do not think about. There's a fuel line, there's rotary valves, there's many, many, many more things. And you can imagine a world in which, for example, the fuel line is made public. Maybe the way you control your speed is you're squeezing a tube of fuel and it adjusts the air-fuel mixture and that changes your speed. But this is difficult because, that's by hiding this, that's one less thing the user has to understand. They don't have to think about fuel-air mixtures. They just think about a certain amount of pressure. The other thing is that they're putting on the pedal. And the other thing is that it means that you, as the car designer, can feel free to change the way the fuel line looks, how it operates, whether there's a fuel line at all, right? So maybe you move from gasoline-based cars to an electric car, and no longer do you want some tube that the driver will squeeze to get fuel. Maybe in some world where that was how people were driving. Now, in an electric car, you would have this fake fuel line, and that would just be silly, right? Okay, so essentially, the point is that if you make a method public, you're declaring to the world, this is something you can use, that you can depend on, that's going to stay the same from now until the end of time. A private method, by contrast, the user doesn't even know it exists. You can delete them, do whatever you want with them. Now we'll see some examples in the near future. We don't know quite enough Java to me to give a really convincing example, but we'll see examples over the next few lectures. Now I'll mention that despite this term access control, it is not about security. It's not about protecting yourself against secret agents or people doing malicious things with your code, right? Nothing at all like that. If someone actually has your code and they're running it and editing it, this isn't going to help in any way. So be aware, access control is really about restricting what other programmers have to think about. That's what we mean. Okay? So public versus private. As motivation for this next part of the lecture, I'm going to ask you a question that I haven't actually taught you how to answer yet, but I'd like you to use your intuition. So let's suppose we have here code that does 4 basic things. First, we create a walrus variable of some type I'm not showing, and then we instantiate a walrus. This is its weight, it's a 1,000 pound walrus, and this is its tusk size, and standard walrus tusk size units, 8.3. Then we create another walrus variable, initially not initialized. Then we set b equal to a, and finally we set b's weight to 5. Now my question for you, using your intuition, whatever language you knew before Java, will this change to b affect a? Okay, so pause maybe and think about it. Okay, so the answer is, indeed it will. Somehow, this second walrus's weight changing causes the first to change. Okay. Another question for you. Consider this. Suppose we have an integer x, set it equal to 5. Now we have int y, set y equal to x, and then finally set x equal to 2. Will this change right here? Will that affect y? Let's think about that. Okay, so in this case, the answer is no. It will not affect it. So what's different? Well, that's going to be what the next big piece of lecture is about. Okay, what is it that's most important? What's the most important difference between these? And why is it happening this way? And if you're interested, you can also check out the visualizer here to get a visual picture, run through these. So let's start by discussing primitive types. So the story all begins with bits. Your computer, it stores everything in memory, right? It has this giant bunch of chips or a spinning hard drive or something. But whatever it may be, there's memory, and your operating system is in charge of managing it, but just suffice it to say, there's a big sequence of places it can put stuff. And most critically, for our understanding, we need to know that all information on your computer is stored as a sequence of ones and zeros. And you probably heard that at some point. And I mean everything, right? Any information is going to be ones and zeros someplace. So all of your emails, your pictures, your videos, notes you write to yourself, everything. Your operating system, it's all ones and zeros. So how can that be? Well, just some examples, right? 72, for example, is typically stored as 01001000. Okay? We're not really going to talk about why today, but just so you know. 205.75 is often stored as a bunch of zeros I'm not showing, followed by this sequence of bits. Somehow that's 205.75. Okay, the letter H is stored often as 01001000, which I'll note is the same as 72. Or true, for example, is often stored as 00000001, and false might be all zeros. So every Java type, there's a different interpretation for the bits. So for example, 01001000 might sometimes be considered H, sometimes 72. And specifically in Java, there are 8 different primitive types, 8 different ways of interpreting bits. So there's bytes, shorts, ints, longs, floats, doubles, booleans, and chars, and these are the 2 we've used so far. Now I'll mention that byte, short, and float you're unlikely to use, but the other 5 will get some use out of. And each of them is a different way of interpreting a bit string. So we won't talk about the precise representations in much detail in 61B. I will never tell you in 61B why 205.75 is this. That's 61C's job. Though we will talk a little bit about integers later. Okay? But suffice it to say, the important point is everything's just a bunch of bits. So let's get a sense of what happens when we actually declare a variable, now knowing what we know about bits. So when you declare a variable of a certain type in Java, a few things happen. 1, well, your computer goes to memory and it sets aside exactly enough bits to hold one thing of that type. Okay? So it says, oh, I need an integer variable, so I'm going to go find some place to put this integer. So for example, an int will get, I'm going to call it a box of 32 bits. Okay, I don't have a better word for it, but box seems good. So now we have somewhere in memory a box of 32 bits. Declaring a double will set aside a box of 64 bits, and each type just has its own hard-coded amount of bits needed. Next, Java creates a list of, or a table that maps every variable name to its location in memory. So somewhere out there, there's memory reserved for this variable, maybe location 0xF8312667 or whatever. That doesn't much matter. And then it records variable x goes in this location. You never get to see that table, but it's there. Java, though, does not write anything into the box that it creates. Okay, so let's say a little visual example. So let's suppose we have the variable x. Okay, so when I declare this variable x, it goes to memory and it sets aside a box of 32 bits. See how many bits could fit there? It's a big box. When we declare y, by contrast, we get this huge box. It can hold 64 bits. Okay. Now, this note here about not writing into the reserved boxes, I'm not showing you what's there, but there's some bits there, right? It's a computer. All the memory has either zeros or ones in it, but I'm not showing you what was already there. So if you happen to be someone who came from a language like C, you know you can declare variables and immediately print them, and then just get the contents of whatever was there in memory. That's not the case in Java. By contrast, in Java, if you tried to actually print out what's in these variables before you assign them, it will say variable may not have been initialized, and it will not compile. Okay? So I'm not showing you what's there, but there's space, and you can imagine that's a place we can put things, and as far as Java is concerned, these are empty. Now when we say x equals some big number, well, then I get a bit representation of this number, and it gets written in there, all 32 of those bits. And likewise, whenever I set y equal to something, now we get 64 bits here. So, because doubles happen to be 64 bits. Okay, so that's what happens when we declare variables, and a little peek at what happens when we assign them. Now, of course, these sequences of bits are really hard for us to read. So what we're going to do in 61B from here on out is use what I'm going to call simplified box notation. So we're going to declare variables and draw a little box here for them. And when we write the stuff that's in memory, instead of writing them out in bits, which we can't read as humans, we're going to write them in human-readable symbols. But I want you to remember that secretly, it's really just bits. When you see this, as far as the computer is concerned, that's what's there. But for our notation, we're going to show this. Okay? We're going to do the interpretation automatically. This brings us to equals. Okay? So what happens when we actually use equals? Given two variables b and a, if we call b equals a, we say b equals a, that means take all of the bits that are in the box a and put them in box b. Okay? That's it. All it means. And that'll be true for everything in Java. And likewise, when you pass parameters to a function, that is, whenever I give us a walrus object over, you're also simply copying the bits. So let's see an example with doubles. So this code right here, we have two doubles, x and y, in our main function. They're just a couple of numbers. And we want to compute their average using this function. So when we run this code, well, the first line of code, we get a box of 64 bits, right? But I'm not showing all 64. I'm giving this nice human-readable interpretation. Here it is. We have one box x, 64 bits, equals 5.5. Next up, we have y equals 10.5. Okay? So now when we look, there's two boxes. We have 128 bits of stuff set aside. And there you go. Next up, we call average. And when average gets called, well, it's going to need its own boxes. So we're passing parameters to a function. So it's as if there's a secret little tiny line here right before that says a equals x and b equals y. Okay? But that happens all automatically, implicitly. So we create two more boxes, and the bit contents are copied directly. Okay? The bits are copied over. The most important point here is that if you're ever confused or uncertain what's going to happen when you use equals or when you pass a parameter, just remember this. It copies the bits. That's it. That's the story of primitive types. So let's move on to reference types. You probably will ask yourself first, well, what is a reference type? Well, basically, it's anything that's not a primitive type. So we said there's 8 primitive types in Java: byte, short, int, long, float, double, boolean, char. Everything else, including arrays, is a reference type. Okay. Now I bring this up because when you instantiate, say, a walrus, there's obviously going to be some memory use, some boxes and so forth. So it's worth our time to look at this and get a good picture of what's happening when we create things. So when we instantiate an object, right? For example, a dog, a walrus, a planet, what Java will do is it will look at all of the fields, right? Here is weight, here is tusk size, and it will create a box for each of them. For the int, it'll be 32 bits. For the double, it'll be 64. And it will, in this case, set these boxes to any value specified in the constructor. Oh, and by the way, if you don't set one of them, it'll be set to some default value, all right? Unlike normal variables. If it's an instance variable, it will get a default value. That's not super important to us in 61B, though. I would say don't rely on them. So when we, I guess as a visual picture, let's suppose we make a new walrus with weight 1000 and tusk size 8.3. What will happen is it creates two boxes, right? One that's 32 bits, one that's 64 bits, and it puts the appropriate information after the constructor is done. Okay, that is walrus construction. Walrus declaration, on the other hand, will be quite different. So when we declare a variable of any reference type, and that's declaring, not initializing, it does not matter what we're declaring. Whether we're declaring a walrus, a dog, or a planet, Java is going to allocate. It's going to create a box of size 64 bits, no matter what type of object. Okay. And now these bits, they will either be able to be set to null, which is all zeros, or the address, okay, we'll talk about that in a moment, of a specific instance of that class. And I'm sure this seems a little vague right now. So let's consider first this null example. So when we say walrus sum walrus, right, that creates a box of size 64, as I set up here. And when we set it equal to null, it copies in 64 bits, filling all of this space. So that's one thing that we can put inside of a walrus variable in terms of the bits, right? We're kind of peeking under the hood in this lecture. Now, by contrast, sometimes we want to actually, of course, make walruses point at a particular object or refer to a particular object. And so in this case, when we declare some walrus, we again get a container of size 64. And when we say some walrus equals new walrus, okay, just as we saw in the previous slide, well, this instantiates a walrus, which we know contains these 96 bits of information, 32 for the weight and 64 for the tusk size. And of course, those 96 bits are not going to fit in this size 64 box, right? You can't put 96 bits in a 64-bit box. So instead, what Java does is it takes advantage of the fact that all memory on your computer has an address, and it writes down where this is in memory. Okay? So maybe it's at address 0xFE112287 or whatever. And so what it will do is write down the binary address of where this object is in memory. And this has really profound and important consequences for how our code will work. So to make this maybe a little more comprehensible, because this isn't 61C. We haven't really talked about memory. The idea of an address of something is probably fairly vague. So what we're going to do is we're going to do the same trick we did before, where instead of showing binary bits, we're going to have a human-readable interpretation. Okay? So 64-bit addresses are meaningless to us, especially since you probably haven't taken 61C. So instead, what we'll do is we'll say all zero addresses will just write null, meaning it's nothing. And then non-zero addresses, we're actually going to represent with a picture, right? So before we were representing some bit streams as like 3.5 or whatever. Now in the box, we're actually going to put an arrow in the box. Okay. So for example, when we say some walrus equals new walrus, well, this thing lives somewhere in your computer's memory. And so what we'll do is write down the 64-bit address. It's secretly this, right? But we're going to represent it by an arrow so we can understand better and have a nicer drawing, right? So here, there's a 64-bit box which contains the sum wall that has an address in it, and it points at this 96-bit. Okay, so that's what's happening under the hood. And so just as with primitive types, or whenever you do equals, or whenever you pass a parameter, we are still copying bits, right? So for example, here, when we say walrus sum walrus, we create a box that's 64 bits. Then a walrus is created, and we point it at this box, right? New will return, you can imagine it as returning the address of this. So we say some walrus equals this, so the bits that correspond to that address, because new has to go out to memory, and it has to dig out little trenches, and it has to put all the walrus parts there. And then it can say, hey, Java, I put the walrus here, and then Java will write down where it was in this box. And now, if we create another walrus variable, it's going to copy the bits. Well, in that case, in terms of our visual metaphor, what that means is we'll just have another arrow that points at that same thing. Okay? So this whole thing, this notation, we often will call in our class box and pointer notation. And it's one variant. There are other variants of this same notation, but that's the one we're going to be using in our class to represent these kind of data structures. Okay, so in short, if we were to summarize everything we've learned about primitive and reference type so far, it is this. There are 9 types of variables in Java, right? There are these 8 primitive types, all of those ones. And then there is the reference type to an object, right? So anytime we have a reference to an object, these are reference types. That's the other type. And in our visual metaphor, we'll use an arrow. And by the way, references, remember, can be null. They might not necessarily be an arrow. And so in our box and pointer notation, each variable is going to be drawn as a labeled box. Here's a labeled box. And we'll put the values in the box. And sometimes those values will happen to be arrows. Whenever we say b equals a, then that means, okay, and again, the simple picture is just that you're copying all of the bits. So if you remember that the bits is what's happening under the hood, equals should be simple. And that same thing happens with parameters. So as a test, to see if that all made sense, to see if you really get it, I want you to think about this question. This is a new question which involves invoking objects, passing things along, and I want you to figure out what will happen. Okay? So think about this question and pause. If you'd like to check your answer, what you can do is click this link, or you can type out that address and use the visualizer and verify that everything works the way you want. Okay, so we're going to round out this discussion by just discussing what arrays do, okay? Because it's basically what we've seen before, but it's a little bit of a different context. So as we've discussed before, when we create an object, we're usually going to use the new keyword. For example, planet P equals new planet, da-da-da-da. And so objects can either be something like that, or they could be arrays. Okay? So both instances of classes and arrays will be instantiated using new. Given that knowledge, what happens when we declare, instantiate, and assign? Okay, first let's discuss declaration. Whenever we declare an int array A, what we get is a 64-bit box, which we can use to store int arrays. But at this point, there's no object instantiated, and there's no default value here, right? If we try and use A, it'll just say undefined. Now, by contrast, when we instantiate, right, what we'll get is a new object, which in this case will be an int array. It'll make a bunch of boxes for 4 ints. So it'll be 32 bits for 0, 32 bits for 1, 32 bits for 2, and so forth. So it'll be a total of 32 times 5 bits. Okay? Now, at this point, I'm calling this object anonymous because the new function, I mean, you can think of it as it creates this and it returns the address. So it digs out space, 5 times 32 bits for all of these numbers. It puts all the numbers in those boxes. But then it yells to the world, I have dug a trench and there are 5 numbers in an array. But in this case, nobody's listening and the location is lost, right? So it's just like buried pirate treasure in your computer's memory. No one will ever get to use it. Now, following the pattern we saw last time, often we will declare, instantiate, and assign an array all at once. So in this case, we create a 64-bit box that can store the int array, this one right here. We create a new object, which in this case is an int array, all this stuff. And then we take the address of this and put it in here. So now the arrow, in terms of our notation, will point at this box. Remembering, of course, that secretly what this thing is a sequence of 64 bits. Okay? And so this object itself, this thing, it's anonymous. So for example, if we were to take A and reassign it to something else, say 345, now this is a drift. No longer are we recording the address of this old array. It is gone as far as we're concerned. We can never, ever get it back. There's no secret thing in Java that says list all of the arrays we've created. It's just unmoored. Okay, so that's reference types. So now, let's see something we can do that's very cool. Specifically, we're going to build our own list, much like, say, a Python list from scratch. Now, for those of you who are steeped deeply in recursion and comfortable with this, it's going to seem very cool. But if you're a little shaky on recursion or maybe haven't even formally learned it, this part's going to be a little intense. But follow along, and I think it won't be too bad. We'll see. So what we're going to do is create a class called intList, which is going to have 2 member variables. One of them is going to be an int, and the other is going to be another int list. Okay, recursion. And then later we'll be writing these methods. So let's try that out. Let's do new class, int list. And as I promised, we'll have public int head and public int list tail. For those of you from 61A and have taken it recently, this would be equivalent of first, and this will be the equivalent of rest. Okay, and if you're not from 61A or you took it a long time ago, don't worry about it. Okay, so we now have a head and a tail. Okay, now I'm also going to define a constructor. And what that constructor is going to do is it's going to be public int list, and it's going to take two parameters, a head and a tail, and this is just for convenience, right? To set our variables just like we've done with planets, dogs, and so forth. So in this case, it's going to look as follows. Head equals h, tail equals t. No big deal, okay? Now let's create one of these things. Int list L equals new int list 5 null, okay? Which is the equivalent, by the way, if you want, of int list L dot head equals 5, L dot tail equals null. But we created this constructor, right? So that we don't have to type all that stuff out. So int list L equals new int list 5 null. Okay. Then we'll do, how about this? Int list L equals new int list 10. And here's the crazy part, L. Okay. I want to create an int list which has 10 at the front and has another list as its tail, an existing tail. Oh, and I should take this away. And then I can go further and say L equals new int list, say 15L. Oops, 15L. And to understand what this code does, I'm going to move it over into the Java visualizer, because without a good visual, this will be real tough to understand. Let's see if there's any bugs. Nope. All right. So when I run this code, what's going to happen is, well, I'm just going to click last so we can see the whole structure. Well, maybe we'll scroll through. Okay. So the first thing that happens is L gets built, and once L is done, it looks like this. Okay, that is the original list. But now we say, actually, I changed my mind. I want L to be something else. I want L to be a list which has 10 at the front and has this old list at the back. So we're going to end up with a new L where the head is 10 and the tail is this list. So we scroll forward a little bit. Okay, I'll just skip all those little steps. Indeed, it is the case. We have a new list where the head is 10 and the tail is the old list. And then if we keep going, now we're going to get something with 15 at the front and the old list right here as its tail. Okay? That is an int list. Why is this useful? Well, it's a data structure that we can grow dynamically. However many numbers we want to stick in this int list, we can do that, right? I mean, it's a little awkward to use. This syntax is hard to understand, and in lecture 4, we'll see how to make int lists more usable. But for now, I want to stick with how we can build int lists generically, right? And it'll be nicer later from a user point of view, okay? And by user, it just means somebody who wants to use a list. Like if this is how lists always worked in your programming language, you might rebel and not like it, but we'll be doing it for today. Okay, so let's say we wanted to get back an item from our int list. Well, as it stands right now, our int list, it's a little awkward to use. So if we want like the front item, we would have to do something like this. System.out.println L.head. Okay, that'll give us the front item. What about the second item? Well, if we look at our diagram, it's L, here's L, dot tail, right? Dot head. So if we say system.out.println L.tail, that is now the second item on the list, or the one after the front one. And if we ask for its head, they get the value. So I guess we'll say prints front item, prints item behind front item. So we try sticking this in the visualizer just to make sure everything is good. Okay, when we do last this time, we get printed out. 15 is the first thing that's printed, and 10 the second. Okay? So that's a basic int list. Let's give our int list a little more functionality, right? Because if we wanted to, for example, calculate the size of our int list, it would be a big pain. So I'm going to write a function to do that so that our users for int lists don't have to go through a bunch of trouble to find the size. We'll do it for them. Okay? So I'll say public int size. And what this function is going to do is returns the number of integers in this int list using recursion. Okay? And that's going to be the cleanest and most beautiful way to solve this problem. So how do we do that?
Well, since it's a recursive method, we want to think about the base case, right? And this is something I'm assuming you've learned somewhere else. So the base case is the simplest kind of list, the list where we already know and don't have to do any work, right? So think about it for a moment, maybe pause and think, how could I test to see if it's what's the simplest kind of list? Okay, so maybe you've pondered. So it turns out that the right answer is if the tail is null, right? If the tail is null, that means I just have a number and then an empty blank. Or, I mean, there's no tail. It's just a list of one item. So I'll just say tail is null. The list has just one item. You might ask yourself, isn't the simpler list that, like, I am null? You know, you might be thinking, like, maybe if this equals null. But if this were null, we would have had a null pointer exception, because you're not allowed to call methods of nulls. Okay? And that's something you'll come to learn, I'm sure, very soon when you start working on project 1. So if the tail is null, in that case, we'll say the size is just 1. However, if the tail is not null, then we have to do some work. In particular, what we can say is we know that the list is of at least size 1, but we also need to take into account all the rest. So maybe we'll look at the picture to help get some ideas. So imagine we're trying to find the size of this list. Well, its size is 1 plus, well, the rest of this. So what we need to do is somehow compute the size of the rest of the list, but luckily, we actually already have that. So using what you've seen before, we're going to make this recursive leap of faith. If we assume that size is correct, then we can say, okay, well, we'll return 1 plus the tail size, okay? And how does that work? Well, it's going to compute its size. And as long as this method works, it works. And that's a thing, hopefully you've seen in 61A. If you have not, it's not going to be one of the core pieces of 61B. I'm not going to reteach it, but I encourage you to go dig through 61A textbook, for example, references, or just experiment with code so that this makes sense. So let's see if it works. Okay, it looks like it should be fine to me, but it's possible there's a bug. So we'll test this one out, and we'll set L.size. So there should be 3. So we'll try running it. Okay, you can see my previous run earlier, and it's 3. So that's great. We can say L.tail.size, for example. It should be 2. Okay, and there you go. That's size. And so I encourage you to play around with the visualizer if this is something that's unfamiliar to you. But I really hope that this is something that seems like something you've seen, if maybe a little shaky on feeling like you could build it yourself. Okay. Now, of course, we don't have to use recursion to do something like this. So I could instead write, for example, public int size, and I'm going to call it iterative this time. And this time, we're going to say it returns the number of items in this int list using no recursion. Okay. It gets 2, let's do period. That's a little sad. No recursion, to me. Okay. Without recursion, what we're going to need to do is somehow step through each piece of the list. And the most common and easiest pattern is to use what I'm going to call a pointer variable. Let's do p. So p stands for pointer, and it's initially going to point at myself, and then we're going to have the size grow over time. So often in iterative code, we'll have a variable that accumulates information. In this case, it's called size. And then what we're going to do is say, while p is not equal to null. That's our way of saying, while we're looking through the list and there's still stuff to look at, then we're going to increment size by 1, and then we're going to say p equals p.tail. Okay? Now, this is not affecting the original list at all, right? And all that stuff we said about bits and equal signs and everything is critical to the understanding of that. This p is not somehow ruining the list, right? You can imagine it seems kind of dangerous, right? I set p equal to this, and then I said p equals p.tail. Seems like that could be a problem, but it won't be, okay? Maybe we'll check it out. Well, actually, yes, let's check it out in the visualizer and make sure it works. We'll do return size. Okay, so let's get rid of this. That's fine. Iterative size, and let's make it the whole list. So this again should return 3. Let's try running it here just to make sure there's no bugs before we visualize. There is a bug. Iterative, size iterative. Okay, close. Okay, it runs, it's 3. That's good. Okay, and we'll take these away. Well, no, we won't. All right, it's fine. All right, so now let's edit our code. Try running it. And I'm going to skip forward to the part where the list is already built because there's no reason to watch that all happen. Okay. Oops, I went too far. Okay, so now we finally get to the point where we're calling size iterative. So let's see how this one works with the visualizer. Okay. So we do size iterative in this case. Initially, p is a variable we're going to create now. We're going to set it equal to this. Okay, p equals this. So this is a temporary secret variable that Java always has whenever you're running a function that's part of a class. And it's just going to copy that address. So p is pointing at myself for now. And then we're going to create a box that contains 0. And this is a 32-bit box. This is a 64-bit box. This is another 64-bit box. And then we're going to say, as long as p isn't a bunch of zeros, then, well, we'll increment size by 1. And then we'll set p equal to p.tail. In other words, we're going to copy the bits in this box. Okay? Well, when we do that, of course, our visual metaphor is that the arrow in p is going to swing around here. And the visualizer, well, it doesn't care. It just spears right through this one, but everything's okay. Okay, we come back up. Well, is p null now? No. Okay, there's still stuff to look at. So then what we'll do is we'll say, okay, we need to increment the size by 1. And then we need to set p and set it equal to these bits down here, which is the address of this. Well, sorry, the address of the final element in our list. I shouldn't say this because that means something in Java. Sorry. So p equals p.tail. Okay, and then finally come back up here and we say, okay, is p null? Nope. Okay, so then we'll increment the size by 1. It's now 3. And now we say p equals these bits, which are of course null. So we'll write null in this box. And at this point, there's nothing else to do. So p at this point is equal to null. The loop terminates. We return size. Here's a return value of 3. And we get 3 printed out. Okay, that's a flavor of the kind of things we can do with int lists. So we will build on int lists and do other things with them next, but that's the core of what makes an int list an int list.
In theory, we could use this data structure we've built to do list tasks. So for example, we could read in all of our students' grades and calculate the median or whatever it may be. However, as it stands right now, there's not a lot of helper methods. And so using this data structure would be rather awkward. We'd have to be referencing tail and head a lot. Our code would look messy. Okay? It would be nice if we had an easier way to get, say, the second item. So instead of having to do system.out.println.tail.head to get the second item, wouldn't it be nice if we could just say l.get1, right? So what I'm going to propose is that you, as a webcast viewer, try and write that method. Okay? So I want you to write a method, int get int I. And it's going to be a non-static method of the int list class. And what it's going to give you is the ith item of a list, where the front item is the 0th. And just to keep your life simple, you can assume it exists. No need to do any error checking or throwing exceptions if you know what that means, right? Let's just keep it simple. So I think the best way to do this is probably on paper, just because that way you don't have to worry about compilation and all that. But if you want, you can also get the code from GitHub and run it and try and check it out, run it through the visualizer. So I will let you pause me and then I'll do it for you. But I would much, much, much rather you actually try it yourself. I want you to get stuck, or not stuck, as it may be, and only then watch. Okay? So honestly, try it out. Pause me. Okay? I'll just stare at you for a second to convince you. I hope you like that exercise. I find that writing recursive data structure has a sort of purity to it that's really nice. It's like doing math problems almost in a way. If you do it recursively, which I now shall. Okay, so let's here create our method. Public int get int I. And what does it do? It returns the ith item of this int list, where front item is item 0. Okay. So as I'd alluded, I wanted to use recursion just because I find it more beautiful. When the code's done, it just feels more correct. It just seems nicer to me. So what I'm going to do is first I need to figure out the base case. And if you are someone who actually didn't pause the video and it's like, I just want to know the answer, well, first I'll just say you're doing it wrong. The manner in which learning occurs, you may remember from my Fanciful Dance Dance Revolution lecture, is by you doing, right? Watching me give away the base case has taught you nothing. So I really want you to have struggled with it. Okay, so that said, all right, I'm just going to keep plowing on ahead. But if I could seize you by the neck and squeeze you, if you had not actually done the problem, I would. Okay, so what I'm going to do here is we're going to consider that base case. So you might have found the interesting point, hopefully observed or maybe got stuck on, the interesting point that has nothing to do with the tail. the natural base case in this example is not if the tail is null. In fact, the natural base case is if I is 0. Okay? Why is that the natural case? Well, one thing that I think is helpful, and one of the reasons I think working on paper is nice, and when you're faced with exam problems, it's nice to have a little drawn-out example so you can utilize all of those fancy visual processing parts of your brain. What happens here is if I'm asking an int list, say L, for its 0th item, okay? So I give you L. Imagine I'm just stating it like this. I give you an int list and I say, give me the 0th item. What do? We just return this. That's all you need. So in that case, the answer is simple. If someone wants the 0th item, we return the head of the current int list. Okay. Then there's the recursive case. I just licked my finger by accident. Anyway, so there's the recursive case, which is say we want the 2nd item, okay, or the 1st item. Maybe that one's slightly easier to think about. So in that case, we can't return this, obviously, so we need to go to the next one to look. So we obviously need to do something involving the tail. Return L.tail, or sorry, not L. Why am I taking L? I am the list. This is this dot head. Sorry about that. So now what I want to do is I want to return something to do with the tail. Tail something? Okay. Well, then I make the observation, and this is the interesting, tricky, mathy observation, which is that if I'm asking for, say, my 1st item, that's this list's 0th item. If I'm asking for this list item number 2, it's this list's item number 1, which is this list's item number 0. With that pattern, then you can abstract code, right? So figure out what the big picture is, and then maybe try and translate it straight into code. But so maybe idea first, code later. That's maybe what I would say. So now that I have the general idea, I want to capture that idea. If I is not 0, then I need to request something from my tail. So I'll say, tail, you go get your I minus 1th item. Okay. And that should be fine. So let's try running this. If we do L.get1, we should get back 10. Maybe we'll take away these prints. Less confusing. Okay. All right. So we run this, and we get 10. Great. And we can try 2. Oops. Wait, no, not that either. What's happening? Okay. Building. All right. Well, hey, something went awry. There went 5. 5. Oh yeah, because my list is backwards, right? So if we look at what our list is, it's 15, 10, 5. That's the correct answer. Yay, we did it. Okay. So I have some more exercises for you that are optional. This week in lab, in discussion, and right now is an opportunity to do more list operations. Okay, so these ones are Inkerlist and Dinkerlist. These ones I'll just put the answers on GitHub, and you can check them out. But basically, I'm going to leave you with this extra challenge because hey, I have your attention, which is I'll describe it to you to maybe nudge you into actually doing it. So imagine writing a public static int list method that goes inside the int list class. Okay, so just to start spoiling this for you, public static int list, okay, etc. What this is supposed to do, oops, my secret recording thing, go away. What this is supposed to do is take a list, say L, we pass in L, and a value X, say the number 2. So if I pass in this list with the number 2, it will return a new int list with every one of the old values now incremented by 2. And, importantly, the values in L are not allowed to change. All right? This is a so-called non-destructive operation. It doesn't damage our list. Okay? And then maybe try out Dinkerlist, which is destructive increment list. So in this case, if I give it the same arguments, L, or this L, and the number 2, it will actually change the numbers in place, and it will return a reference in this case. So if I said Q equals Dinkerlist, it would point at this. Okay. So try that out. There is code available. In this case, I don't know, you could do paper, you could do on computer. I'm not really sure what's best. Basically, it depends on what you prefer. And there will be solutions in the webcast. In the GitHub repository, and of course the discussion and labs this week will have more problems. Okay, so that's the core of int lists. What we're going to do next time in lecture 4 is see how we can make int lists even better and more comprehensible to the person who ultimately wants to use them. Okay, that's it for today.